molecular cloud. It's a big nebulous area that stretches from most of Orion into Eridanus.
Right.
And that stretches for thousands of light years.
Oh, okay.
So the Orion Nebula that you see is just part of the overall.
So what I'm
Orion
gonna
cloud.
say is, I looked at, I found 61 fanned out, that was interesting, but I need to do more research.
The orientation is so intense that as the stars are flying by the area, they're gauging the game of gravitational billiards.
Excellent, yeah.
Because as they fly by each other, it's going to feel the gravity. So you're getting clusters of stars that are knocking around each other without actually making physical contact. The gravitational game of knocking around the stars.
So rather than,
Oh, yeah.
Dave, this was a couple of years today, you'll explain it to me.
Right after I
Why
get
not?
this week, so,
Yeah.
it's kind of a big key to the,
Yeah, yeah, all the FAA inspectors, couldn't find a single one on Monday and Tuesday.
yeah.
Just so we had, talked to one of them, called me home, and he said, well, we got a couple extra days off.
Yep.
So-
Yeah, it is surprising. It's kind of funny, they give it to you after we submit all of our documents.
Oh, yeah.
The
No.
stars usually here when land figures out.
Okay, because I know they were at UA for a while, but they weren't supposed to be for.
Well, we didn't have it in the last 2 months face to face because of the classroom issues at ACC. But
Which campus?
it's in the Midtown campus.
It's-
The Victoria, I mean,
Oh,
it's the Midtown.
Yeah, as soon as he, lets me know.
What's now known as
I'll get it
HTC
Friday.
College.
oh, not HC.
It's still HTC, but it's not a community, it's a city college now. So hopefully I'll be teaching there in February, for that, along with teaching here.
Nice. Did
We'll be starting shortly.
Calling technical support.
He's the tech support. We're getting ready to start.
Oh,
Okay. You wanna, you got something to say, or?
I can tell them about the thing.
We'll do that,
Do it later.
yeah.
Hey, is it on this?
Like, just,
I think I'm just talking.
oh, like you want, no, you can stand right here, just stand right there, and you can point the screen from here.
Oh,
Do you need
okay.
to show
Will they
you?
see it though?
Oh, yeah. Who's they?
People in.
Oh, online, no, you'll have to use the mouse.
Oh, okay.
I'll show you, it's easy, you just use the,
Yeah, I
It's
know,
just
but
a-
I won't.
but in here you can use it.
Oh, okay, okay.
You up and running?
I don't know. I'm not getting any audio. Nothing looks wrong.
Four people online.
What's that?
Got 4 people online.
Yeah, probably.
Yeah, it's okay. It's working now.
All right. Y'all ready to get started? You good? All right. Hey, everybody. Sorry for the little bit of a late start. I'm Brandon Riddell. I'm not Doug Holland. So Doug's staying home today to help his wife out. But welcome to the 2026 kickoff for JSC AS, our January meeting. So thanks for coming. I guess the tradition's always, I look around, we kind of have a small crowd tonight, but I see a couple faces I haven't seen before. Is this anybody's first time here? You too? Okay. Yeah. How did you find out about the club? We always ask him, what kind of interest do you have in astronomy?
I just read about this meeting in the morning roundup email at JSC.
Oh, okay.
Thought it would be cool to come see.
So you work on site then?
Yes, sir.
Okay. What group are you in?
Ethos and MOD.
Oh, okay. FOD. Nice. I work in engineering over there, so maybe we'll cross paths sometime. Next to you.
This is my husband, Adrian.
All right, nice meeting you. Thanks for coming. Anybody else? I think you guys, you good?
We've been here.
Yeah.
for,
Okay.
3 times.
3 times? All right.
Third time, but-
Hey, you're starting the year off right. And up front here, you raised your,
Number 2.
Yeah, number 2.
Second time.
Okay.
I came last month and
Yep.
lot of information.
Okay. Well, welcome again. We're kind of starting off the year. So this is the agenda we have for tonight. What if you guys remember, and for the new people, we always have a kind of a main speaker, and then we'll have a short break, and it's a good time to go around, meet, talk to people, but it's pretty short. And then we'll do a couple small talks after that with Star Party News, and Rick Slater has a talk. And then we have this meeting after the meeting. A lot of us go up to Mod Pizza. It's a great time just to share astronomy talk and whatever else space news, and just get together. So everyone's welcome to come to that after the meeting today. Let's see here. I just want to we'll jump straight in and let's bring up Annie Wergitz. Sorry, this is my first time doing this. So Annie and whoever else is speaking, I think you, Rick, you got to use the mouse pad. And so one final reminder, I don't think it's gonna be too bad today, but sound really carries in this room. So when the speakers are talking, just try to keep the conversations quiet, and that'll make it easier for the speakers. Yeah, go ahead and come on up, Annie. And so while she's coming up, I want to read her bio. You guys may remember she showed up last time and gave a short talk. So Annie Wergitz is a lifelong space enthusiast who's on a mission to get everyone excited about space exploration. Annie holds an undergraduate degree in communications from the University of Houston. She holds a graduate degree in space sciences from the University of North Dakota. She's focused her graduate studies on human spaceflight, including mission and spacecraft design, as well as life support systems. She's also passionate about heliophysics, something I am too, and anything related to the sun and space weather. So please give a warm welcome to Annie.
Oh, they changed it. Okay.
Yeah. Oh, okay.
Oh, well,
I was just going to show you. Yeah, that was the right presentation, right?
yeah. Okay. Hi. It's always weird hearing someone talk about you when you're standing right next to them. It's like, yeah, that's me. Thank you guys for having me back. I'm super excited to be here. A little bit about the program that I'm in with NASA. So I'm at the NASA JPL Solar System Ambassadors, my badge. And we're volunteers. There's about 1,200 of us. JPL is who runs the program, and we get to do things like this. Next week on Friday, I get to show some kiddos in my neighborhood about the solar system. The week after that, I think there's a star party. I was going to come out there and see if you guys wanted some help with that. But it gives me an opportunity to share my passion. And it feels a little redundant to say I want to get everyone excited about space. This is an astronomy club. Y'all are already excited, or you wouldn't be here. All right, so So the problem for me is always that I get 45 minutes to tell you about a mission I've been following for effectively 7 years now. So it's really hard to distill it down into the things that I want to I want to share everything. So I'm going to do my best to get it done in 45 minutes. And I have my notes to try to keep myself on track. So yeah, I went a little cheesy with the title, but there's a reason why I picked that one, and it's the whole reason why the mission exists. So to boldly go closer to the sun than ever before, the reason why the mission exists is because that's what we needed to do to answer some fundamental questions. I'll get into that in a minute. I kind of wanted to start it out by telling you a little bit about when I decided to go to graduate school. I was laser focused. Human spaceflight is everything. I'm going to do life support systems, mission design, spacecraft design, human spaceflight physiology. Everything else is boring. And then I got up there and I was like, oh man, asteroids are actually really cool. And then a friend of mine took me out aurora hunting, and I was like, oh man, I'm hooked. So I wanted to change my course of action, but it was too late for a trajectory course maneuver on that point. So before grad school, I did not realize that the sun was this dynamic, churning ball of plasma that is more than just the thing that gives me a sunburn and helps our plants grow. It's 11-year cycle. As the more I started learning about it, the more I was just like, man, this thing is fascinating. And we just think of it as this glowing thing in the sky. And living in Houston in the summertime, sometimes we're not happy that it's there because it's 110 with 3,000% humidity. So I'm just learning once I got to grad school just how it's really not boring at all. The other great thing about living up north is there's actual seasons, and it gets cold up there. And there were times where we didn't get above -20, which was great because it makes the atmosphere do really cool things. Like I know we get crepuscular rays down here, which is what you're looking at on the left, which is essentially shadows cast by the clouds that are over the horizon that you don't see, for lack of a better explanation. But because where I was living was so flat and there were no buildings at all, you could just see as far as possible, like in every direction. If you look at the picture on the right, my next door neighbor was a crop field for sugar beets. So I had an uninterrupted view out east. So I got to see tons of crepuscular rays. The thing on the right is called the sun pillar. If you've never seen it, it is magnificent. I was outside and forgot to put my gloves on. As you can see, there's snow, and almost gave myself frostbite because I was just not paying attention to how cold I was getting. I was just snapping a bunch of pictures. And sun pillars are just magnificent and glorious. The other really cool thing I got to see were tons of sundogs, which we don't get lots of those down here. The funny thing is this is not my picture, but this is from Fargo, North Dakota. If you go look at the Wikipedia page for sundogs, it's this picture from Fargo, North Dakota. So having my friends in atmospheric science explain the arcs in the sundog and why it appears at certain angles, it was just further fueled my passion for the sun. And of course, the thing I haven't mentioned yet that everyone always asks me about, if I lived up north, did I ever see an aurora? We actually had a hotline and we would go aurora chasing. So we were the space sciences and our next door neighbors were the atmosphere science folks. And it was a great team because they had all their fancy doodads saying, go this way because here's where there's no cloud cover. And we're like, well, the aurora that way. And we went and did a lot of aurora chasing. I happened to be up there during Solar Max. So my friend gave me a glow stick and then he grabbed it from me, told me to hold still, and he was doing stuff behind me. I was like, what are you doing, Jonathan? And then he shows me this picture and he had drawn wings on me with the glow stick in a time lapse. He had all kinds of really cool ideas for photos with the aurora in the background. So I just remember the first time seeing those, and my friend was going off about something called a KP index. I'm like, I got to know all this stuff. So back to the reason why I'm here tonight is to talk about the sun, just to reiterate and hopefully get you as excited about it as me. Is just that thing out there is just fantastic. And every dot in the images that y'all take with your telescopes, every dot in the sky that you see when you go on your Messier marathons, those are just not, if more exciting and dynamic as our average star. It's not average. In my mind, I'm biased. So I really am excited about this mission, and I hope some of that excitement gets you excited and you learn more about the Parker Solar Probe mission. So a few years ago before the launch, Nikki Fox, who was the associate administrator of the science directorate at NASA at the time, she's now in a different directorate. She's a principal scientist on this mission, and she came to Rice and she gave a lecture, and I was writing down every word that she was saying, and I was fangirling, I'll just admit it. She had a Parker Solar Probe necklace. Her dress was made out of material that had the sun on it and everything, and it was just captivating to listen to how excited she was about this mission and hadn't launched yet. So my goal in this is to do the same thing for y'all, because I'm just over the moon. No, we're not going to say that. I'm excited about this mission. Okay. So
the mission commander.
I'm sorry?
What would her, as far as her involvement, how is she connected to, like, would she be like like commander or the leader of the mission?
Oh, no, she's not principal investigator. She's just she's a scientist on the mission. So she does, heliophysics and astrophysics and science in the science directorate at NASA, but she's not, managing it. I forget what her role is now. She's moved a few times since 2017.
So the top person in NASA would be the director, right?
Usually they're called principal investigators on a science mission, but I'm not sure who that is. I know the mission is at Johns Hopkins APL. I think Harvard did one of the instruments. There's a couple of organizations involved. But I do think that the main NASA center is Goddard. So I can give you some websites if you want to learn more. I don't happen to know the name, sorry. So in thinking about a title for this, I thought, what is the main point of this mission? And, Star Trek, to boldly go. So the question that I think, the first question, because all science missions are to answer questions, the first question we should ask is, why? Why do we need to boldly go closer to the sun than anyone's ever gone before? I think this is obviously the most important question to answer because it explains why for 60 years scientists have been trying to make this mission happen. And the answer that it finally technology caught up to where we can have a heat system that will protect the spacecraft so that it can go to the sun. And that's why we have the mission now. The reason why you might be asking is we have an entire fleet of heliophysics missions. Any of you also fans of Solar Dynamics Observatory, SDO? Okay, that's fine. They have so many filters on that. It's a space telescope and it's got tons of filters on it. You can see the sun in all different kinds of wavelengths and then they stack them. The imagery on SDO images are just fantastic. You should go check them out. I have SDO posters with me, by the way. ACE, which is monitoring it's at the Lagrangian point, so it's at a specific point between Earth and the sun. And ACE is probably one of the first spacecraft to encounter particles that are coming at us from the sun. And so it measures all the different energies. So when you hear about geomagnetic storms and things like that, ACE is one of our first points of contact to know what's coming at us.
So that's the red dot right there.
ACE. Oh no, I don't know where the red dot is. Where's the red dot? Oh, that's this thing.
Okay.
No, I have circles around the ones I'm talking about. And then there's SOHO, again, fantastic imagery, and Stereo, which Stereo was a 2 spacecraft mission, Stereo A and Stereo B, and they launched at the same time and they went in opposite directions in Earth's orbit. And it was the first time we got a 360-degree view of the sun. And then they kept going, and unfortunately we lost contact with one of the Stereo spacecraft. So IRIS gave some fantastic high-resolution images of the surface of the sun, and you can see the granules churning. So if we have all of these, why do we need to go there? Why do we need Parker Solar Probe? And the reason why is because the questions that we have about the sun can't be answered by viewing it from afar. We've known for a while what kind of particles arrive at Earth when there's a solar particle event. What's the composition and speed and origin of those particles when they leave the sun? Well, you can't measure that at a Lagrangian point close to Earth. Some of the questions about the solar wind. What does the solar wind look like when it's created and it comes off of the sun? What is thrown off the sun but never arrives at Earth? Well, you can't do that measuring it from afar. The only answer is to go there, right? So I'm trying not to do just facts. I want to tell a story here, but sometimes you have to stop and explain some of the facts. So this is the first mission from all of humans, all of us, to fly through the atmosphere of the sun, the corona of the sun. And it's the first NASA mission to be named after someone who was still alive. Eugene Parker, who back in the 1950s was a scientist who he hypothesized and theorized that there was something called a solar wind based off of his study. So the mission was named after him. He was actually at the launch and he was sitting front row with Nikki Fox. Unfortunately, he passed away in 2022, but he did get to see the mission with his name on it launch, which how surreal would that be? And so it's a particle physics mission. It's to study the particles that are coming off of the sun, the magnetic fields, because that's a huge player in the direction and velocity of the particles, and also the magnetic fields, the particles, and just the electric fields, and all of the velocities of everything and the composition of everything. Okay, so the three main questions that Parker is seeking to answer is the coronal heating problem. If you look at oh, that's on the next page. I'm getting ahead of myself. So there's three problems, the coronal heating problem, and then the origins of the solar wind, which is what I mentioned. So the solar wind is a constant stream of particles coming off of the sun. I know we think of those coronal mass ejections and those big, huge particle events getting thrown off, but in the background, there's constantly particles coming off of the sun, and nobody's really ever known why or where or how they originated, and also why they accelerate after being thrown off the sun. And then just studying the solar energetic particles, their composition, and how they are perturbed by the different magnetic loops and things like that. So just studying the composition and the types and the nature of the solar energetic particles. So when we talk about the coronal heating problem, if you look on the right, if we start at the center of the sun, obviously it's going to be very, very hot. It's 27 million degrees. That's where fusion happens. And as you move away from the center of the sun, it gets cooler. I mean, it's still 30 or 3.5 million degrees. Not a good day if you're in there. And then it gets down to about 10,000 degrees. And it's the 10,000 degrees is the photosphere. That's the layer that we can see when not with our own eyes. Don't look at the sun, but the visible layer in the visible range of the spectrum. But as soon as you leave off of the sun, it starts getting hotter and hotter and hotter. And by the time you get to the corona, or the atmosphere of the sun, we're back at 2 to 3 million degrees Fahrenheit. And so, in order to understand, well, why is it getting hotter as you move away, right? That doesn't feel intuitive. It should be getting cooler. And so again, to study that and figure it out and look at what particles are there, you've got to go fly through it, right? And that's what Parker Solar Probe has been doing, is literally flying right through that corona, the atmosphere of the sun. I think there was a gentleman here, there was a gentleman here last month. And one of the talks that was given was why the sun really matters. And yeah, we know we rely on it for crops and weather phenomena, but he talked about the other aspects that are impacted by solar weather, those energetic particle events, solar wind and things. It's a bad day in space if there's a solar particle event, especially when you're talking about for astronauts. In fact, the areas of the International Space Station where the astronauts spend the most time, so the areas where they're making their food, the areas where they're sleeping, those are actually more heavily shielded from particles. There's more radiation shielding around those than the rest of it. They're still getting particles because they are above a huge portion of our atmosphere and whatnot. But in a few weeks, maybe, or in a few months, depending on when it launches, Artemis 2 is about to happen. And there's going to be 4 astronauts aboard the Orion spacecraft who are going to be outside of the Earth's magnetic field protection, and they're going to be out there for 10 days. You don't want the sun throwing off high energy solar particles while they're out there. So in order to know if that's going to happen, we need to know the nature of these things, and really we just have to study it, which is what we're doing. So it's not great for astronauts. It degrades materials out in space. If any of you guys have ever heard of the big hockey outage in Canada in the 1980s, there was a solar particle event and 3 of their communications satellites got knocked out, and the country was upset because they couldn't see the end of the hockey game. I'm not making that up to be dramatic. That's what the news said. So if you have a high energy event and you don't put your spacecraft or satellites into safe mode and lock it down a little bit, it can build up a charge and destroy systems on that satellite. And I can't get anywhere without GPS, but it's not just GPS to help us navigate and get to the restaurant we're trying to go to. Tractors now are GPS driven. trains, planes, all of them rely on GPS signals and coordinates for, for transportation. Think about freight, think about like produce, think about all of the things, not just like, flying somewhere for fun. That kind of thing is used for, infrastructure. Oil rigs and electrical lines can build up charges and get knocked out. When there was this huge solar particle event in the 1800s called the Carrington event, and it fried most of the telegraph wires because the charge built up on the ground during that event. So it's not just they're pretty aurora to look at. It can cause tremendous damage to our infrastructure, and we really need to understand, not just for the astronauts' health sakes, but our infrastructure, what's going on with these events so that we can get better at forecasting them and understanding them, so we know when to put these satellites in safe mode. Yeah, I wrote, don't forget to say something about Artemis 2 now. Okay, so let's talk about the probe itself. I took this a few days ago when I was getting ready to turn my slides into Doug. And this is its current speed. I forgot to change it out of metric. Sorry about that. So a couple of days ago, it was at 33,000 miles an hour, which sounds slow because I'm getting ready to tell you how fast it can go, but it's still 2 times the shuttle, right? Shuttle was 17,500. And it has gone 5.2 billion miles since it launched in 2018. And the reason why I mentioned the speed is as it's going on an orbit around the sun, and I'm going to show you an orbital diagram, but as it gets closer to the sun, it speeds up. This spacecraft is the fastest human object ever built. Does anybody want to guess how fast it went when it got close to the sun back in December of 24? 63,000? It was 430,000 miles per hour. It can cross like a huge portion of the United States. I think it could go from like London to Tokyo in a minute or so. I read so many analogies, I can't remember any of them now, and math's not my forte. But yeah, 430,000 miles per hour, and it set the Guinness Book of World Records for that. You can actually go look at the Guinness Book of World Records, and Parker Solar Probe is in there. And what's funny to me is on the entry for the thing, it said location not applicable. I thought that was funny. Why don't you just put outer space? So the spacecraft's been out there, like I said, since 2018. Right now it's at a cool 54 degrees C. And when it gets closer to the sun, obviously it's hotter. So all of these numbers that you're seeing right now are because it's almost at Venus's orbit. It's outbound right now. When it gets closer to the sun and it's doing its fly through the corona, the numbers get really high, obviously. The other thing I would be remiss if I didn't mention is, why is it a good time right now that Parker's out there? And it's because we're at solar maximum, or the time in the sun's cycle when it's the most active. So the sun has an 11-year cycle of ups and downs of activity, and it's been measured since the 1700s. And right now we're in a solar cycle maximum, or solar max as it's known. So there's lots of activity, which is great because we're getting lots of really great data from those active regions and seeing what's coming off of them. Okay, so you're gonna go fly through the sun's atmosphere, and you're gonna study the particles and the magnetic field, the electric fields. What do you need to study all of that? And it wouldn't be a proper space talk if I didn't geek out about the instruments on board. So there's 4 main scientific instruments on board the spacecraft. And by scientific instruments, I'm talking just science stuff. Obviously, it has solar panels and batteries and thrusters and, a frame and things like that.
Detection and measurement equipment.
Yeah. So it's things to capture the information that we've been talking about so far. Yep. Antenna, it's got to talk to Earth and receive commands from Earth. So those basic communication systems. I'm going to focus on just the scientific instruments. So there's a story that I'm building here. So I'm going to start with SWEEP. I think it's cool because it sweeps through the atmosphere. That stands for solar, wind, electrons, alphas, and protons. And that specific scientific instrument is a suite of 2 different instruments. It's the SPC, which is the solar probe cup, because it catches particles in its cup. You can see it being pointed to right now. It's above the heat shield. So that is exposed to the full brunt of the heat during the fly-throughs of the atmosphere, and it has to be because it's got to capture the particles. Brave instrument there. And then you have the sweep span B, which is the solar probe analyzers, and that is also capturing the particles on the back end of the spacecraft. So it's looking at, the one that's exposed to everything and then the one that's not so exposed, and they're comparing the two particles that it's capturing. It counts electrons, protons, helium ions, and not only that, their quantity, their velocity, and their density and their temperature. So it's capturing all of that and studying that. I'll talk more about the thermal protection system because that's the thing that everybody wants to talk about is how does the spacecraft not melt? We're going to get to that, I promise. It does have a liquid cooling system inside as well. We're going to talk about that. And the really cool thing about this is if you look at any other spacecraft and you see their solar panels, they're usually fixed. The Parker Solar Probe solar array actually retracts and pivots to get behind the heat shield when it's at close approach. But the really incredible thing is like, oh, okay, well, it's behind the thermal heat shields when it's flying through the corona, so the spacecraft is surely running on battery power. The answer to that is no. There's a very small tip. If you look at the end of the solar array, there's a very small tip of it. I'll get to you in just a second, I promise. That is stuck out and actually still in sunlight. And that is still enough to power the entire spacecraft. It's actually more than enough to power the spacecraft on close approach. So it doesn't rely on battery at all on close approach. The rest of the solar arrays get tucked in, and there's a tiny piece that can stay out and collect enough sunlight to run the whole spacecraft at close approach. Sorry, yes?
Is it possible for you to use the laser pointer to show what's retracting?
Oh, yeah. I forget that I have a laser pointer, sorry. So this dark part here, there's going to be other images of the spacecraft in motion, so you'll kind of see it better than a static image. I apologize for that. So this dark area is the solar panel that's tucked in, and then the light part right here is what's sticking out from behind the heat shield and getting sunlight during the close approach.
So that folds in during the approach.
It is folded in this picture.
Oh,
Yeah. Usually it's out like this, and then during close approach, it's tucked back in. It's hard to explain these things with static images. I have some videos that will do a better job of explaining that. And if you guys have questions, please do raise your hand. I'm all too happy to stop blathering to answer questions. Okay, so SWEEP. We're talking about a particle physics experiment. We've got SWEEP. Let's move to the next couple of instruments. So the first one I want to talk about is pronounced ESIS. That symbol in between the IS and IS is the astronomical symbol for the sun, but it's pronounced ESIS because I'm like, I don't know how to pronounce that. It's ESIS. It stands for Integrated Science Investigation of the Sun, and they put the sun symbol in the middle of the word, which is cool. As its name implies, the Integrated Science Investigation of the Sun. And this is another particle physics instrument. So it has two pieces, EPI low and EPI high. The low and high refer to the energy of the particles that piece of the instrument measures. So, and there's still high energy, but it's low and then high. So the low, so basically these measure the electrons, protons, and ions. And they're looking at not just the quantities and things like that, they're looking at the life cycle of those particular particles. So essentially, this is how we figure out what does the solar wind look like at the sun, and then what is its characteristics by the time it gets to Earth or like ACE or one of the other satellites. So this is really the one that's looking at more information about those particles to understand the solar wind. This is looking at a broader amount of particles, so bear with me on that. So it measures the spectra to identify things like oxygen and silicon, and I think neon was one of them. And so it's looking at the quantities and things like that of those particles. Then the EPI high measures particles with higher energy that low obviously can't detect. What's really incredible about both of these is that they can detect up to 100,000 particles per second and take measurements on all of them, which that's mind-boggling. And it's doing it while it's flying through that chaotic environment up there. And these are particles that sweep can't handle as well. So you're really trying to cover all of your bases with what are the particles that we're encountering at the sun, in the corona, and along the, it's not just during the time during the fly through the corona, it is taking measurements all the time. The ones in the corona are the most exciting in my opinion. Okay, then we've got fields. And fields are the four sticks coming, oh yeah, I have a laser pointer. The four sticks coming out of the heat shield there. And then it's also this big long boomstick coming out of the back of the spacecraft. And the reason why you have four and then one coming out the back is it gives you a 3D model of what you're seeing. And fields is looking at electric fields, hence the name, and magnetic fields, hence the name. So it's looking at throughout its orbit, and especially while it's flying through the corona, it's trying to measure and understand the fields associated with things like the waves, the shocks, the magnetic reconnection. So when the magnetic loops on the sun touch each other and they reconnect and you get an explosion, it's looking at, it's trying to measure the magnetic and electric fields around those types of phenomena to try to understand, is this where a fast solar wind comes from, or what is this contributing to everything? I had to look this up because what are these sticks made of? Because they are outside of the heat protection of the heat shield. And it is a niobium alloy. I couldn't tell you what that is, but I had to look it up. And those can withstand 2,500 degrees Fahrenheit. The fifth boomstick is also where the magnetometers are, but really all four of them or all five of them combined to make a 3D model of the electric and magnetic fields. So lots of particle physics and lots of electric and magnetic fields, and it's great, but you don't know where you are when you took those measurements, right? You want to know what you were flying through when you took those instruments, and that's where WSPR comes in. WSPR is the only imager on the spacecraft. The really cool thing is WSPR is kind of like a driver in a car. It's looking at where it's going. So the spacecraft flies around the sun like this to keep the heat shield obviously in between the spacecraft and the sun at all times. And WSPR is looking that way in the direction that the spacecraft is going. So essentially, WSPR gathers the images, and then the spacecraft particle physics experiment scientific instruments fly through what it just imaged, and then you're like, oh, okay, so we saw this happen, and then we flew through it, and this is what ended up happening with all the particles. So WSPR is really integral in the aspect of, okay, we see a phenomena, we fly through it, and okay, now we understand why that particle changed, or there was a velocity change, or what happened here. So that all of those scientific instruments play a huge part in supporting each other, and then WSPR is really the thing that ties it together of, okay, now we know we were in this phenomena when all these different particle measurements changed. Okay. So I'm gonna take a pause. That was a lot. I know it was a lot of engineering and science. I can't help myself sometimes. Are there any questions about any of that? I'll do my best. If I don't know, I'm happy to say I don't know. Yes.
Just fine. You said that I guess the signature from the sun till it gets to the earth with the particle.
The signature, I'm not sure I understand signature.
Well, signature being the way the particles work and everything when they come off the sun.
Okay.
And their change, what do they look like when they hit the earth?
Right.
Okay. What have you found out about that so far?
That is the last half of my presentation.
Well, I guess I'll hold my
I have done my best to distill several years of scientific discoveries into what I can contain in this presentation. So I feel like a few of them are going to get answered, but if I don't, let's circle back during the break or something, because I want to make sure I answer your question. And if not, there's a great plug to go to their website afterwards.
What WSPR stands for?
Oh, no, I did not. Did I write it down? Yes. Wide field imager for Parker Solar Probe.
So it's basically like a camera.
Yes, actually, it's two radiation hardened cameras, and you guys are all the photography people here, so I'm not going to understand this, but it doesn't use CMOS; it uses something else because it's more radiation hardened. CCD. Thank you very much. Charged coupling device. Yes, I remembered. Okay, I don't know what it means, but I remembered it. Okay, so the moment you've all been waiting for. This stuff is flying through the corona. It's hot. We know that. How does it not melt? And that is the thermal protection system, or the TPS, not the tire pressure system. Okay, so the first picture on the left that you're looking at is the frame of the spacecraft, and we're building out from there. So the next picture in the middle, the TPS, or the heat shield, I'm going to call it heat shield from here on out. The heat shield is sitting on top of the frame. It's been mounted to the frame at that point. And then the next part, those black cones kind of, that is going to be some of the radiators and whatnot with the thermal protection system or heat shield. Radiators being not like, well, it helps get rid of heat in space. We'll go with that. Excuse me. So the heat shield that you're looking at, that black sheet that's on top of that frame, that is the piece of technology that once we knew how to make that specific type of carbon compound that would keep the spacecraft from melting, that's what gave the go to do the mission. Because before that, it would have melted, right? We just couldn't have gotten close enough. The instruments would have been overloaded with heat or radiation. So the crazy thing about this, and I'll give you the numbers in a minute, the heat shield, when it's at close approach, is several thousand degrees. The rest of the spacecraft is at room temperature. That's how good of a job it does in protecting the spacecraft from the heat. So this is, yeah, well, there you go. I spoiled my next slide. So the thermal shield is the part on top. I'll give you some figures for that. It's 4.5 inches thick and then 7.5 feet wide at its widest point. Where did that another? Okay, so 7.5 feet wide, and the part behind it, the spacecraft kind of narrows down to 3.5 feet. It's kind of tucking in there behind the heat shield so that it can be protected on close approaches. And it's 9.8 feet from the heat shield to the back of the main spacecraft, not the magnetic boom, but the rest, the other part. Okay. And I mentioned the liquid cooling system and the radiators. So I forget how many gallons of water it is, but there's a few gallons of water, not too many because water is heavy and you need to worry about weight in space or mass in space. But there's tubing system through the solar arrays on the backside of the solar arrays and throughout some of the other aspects of the spacecraft. And it's constantly circulating and picking up the heat, and then the heat is radiated out into space to get rid of it. Have any of you ever seen the liquid cooling ventilation garments that the astronauts wear? So they wear this suit underneath their spacesuits that has a bunch of tubes on it. It's the same concept. The water is flowing through there and gathering heat that's coming off of the astronaut underneath their spacesuit, and then it's radiated out so they don't overheat. It's the same concept. The spacecraft has a liquid cooling ventilation garment. Counterintuitive because there's a lot of electronics, but water stays in the tubing. Okay. I'm always a big fan of pictures of spacecraft with humans in the same picture, because otherwise you're like, is this, I just told you the figures, but does that give it context? Not really. So this is when she was all buttoned up and getting ready to get shipped down to Florida to get launched so she could go on her mission. And I love that there's humans in there so you can kind of get a picture for the scale. Obviously, solar arrays aren't out. The magnetometer boom is not out. It's all packaged up in that special paper to keep it protected. But I just always love those pictures where there's humans there for scale. And if you've ever wondered how do you get an entirely assembled spacecraft from one place to Florida so you can launch it, you just catch a ride on a really big military plane. I had to get help figuring out what plane it was because I forgot to bookmark the websites where I got these pictures from. It's all on NASA's websites, but it's a rabbit hole and I go wandering. This is the C-17 Globemaster, aka really big military plane. So they put the spacecraft inside of that box, and they load it onto the plane, and it flies it to Kennedy. Okay. The other awesome thing about this mission is it launched on my favorite launch vehicle. I have a little plush Delta IV Heavy that I've had for a really long time. So Parker launched on a Delta IV Heavy. There's it on the rolling up to the pad. I really want to say that that's Venus there in the background. I think that would be poetic since it used Venus flybys to change its orbit. I don't know that that's Venus. If it's in the morning, it might be, but I don't know. Or Jupiter. I like the poetry of thinking there's the two of them and they're going to meet soon. I tried really hard to find when this was taken. I kept seeing the person's name who took the picture on behalf of NASA, but I couldn't find what it was.
For those of us that don't know about the ships, is that a government ship or a commercial ship?
So this is the United Launch Alliance, and it's one of the companies that NASA contracts with to launch spacecraft on. So there's the Delta IV Heavy from the ULA. We have the SpaceX rockets from SpaceX, obviously. James Webb launched on an Ariane 5 or 6, and that's the European Space Agency launch vehicle that launches out of French Guinea. Or I'm really bad with the name on that one, but
Karu Space Flight Center in Michigan.
that. JAXA has some launch vehicles of its own, and I know there's a couple of other, like there's the other launch vehicles. But to answer your question, it's one of the vehicles that they contract with the launch
So it's
vehicles.
contracted out from the company.
Mm-hmm. Yeah, United Launch Alliance.
The ULA is a consortium of Boeing and Lockheed Martin.
Yes. I thought that's what it was, but I didn't want to say it because I didn't want to say something that was wrong. No, it would have to be, you know what? I don't want to guess because I don't want to be wrong. I was 38 and 40 and 44. I don't know. That's one thing I didn't write down.
So then you tried to call Jupiter is a street line.
No, not that. This up here.
Yeah, okay.
Yeah. I promise you I know what a street light looks like. It's not a street light. I was pointing at this because it is in the part of the sky where Venus would be if that's sunrise, but we don't know when this picture was taken. Or it could be Jupiter. Yeah. I don't know. I tried to find it out. I spent way more time than I should have trying to find that. Okay. All right. I have a quick video for you. There's no sound. But this is what a Delta IV Heavy launch looks like. Those flames are planned for. That's a normal part of the launch. And so it launched in around 3:30 in the morning in August of 2018. It was a beautiful launch. So then gets into outer space, the fairings separate to reveal the spacecraft once it's above the atmosphere. And then it's separated from the upper stage, and then it's sent on its way by the last upper stage, I guess. And then it's separated and it's on its way. The next thing you'll see is the solar panels will unfold. So there you go. There's some video of what the solar panels look like, fully outstretched and outside of the heat shield when they're out. And there's the magnetometer boom. You can see the SPC sticking out from in front of the heat shield. There goes the 4 fields antennas. And she's sent on her way. All right, I do want to take a minute to talk about the orbit because it's an interesting orbit. Usually when you launch a spacecraft off of Earth, you borrow energy from the Earth from its rotation. That's why we launch around the equator, because you get the most energy that way. But in this case, Parker is launching with energy in the same direction that our orbit is. So if you didn't change the velocity of the spacecraft, it would continue to go around the sun, but in the Earth's orbit. And that's not helpful if you're trying to get through the corona. So essentially what they did was they used a series of Venus flybys, and essentially the spacecraft gave energy to Venus. It used Venus's gravity to not speed itself up. Usually when we hear about gravity assists, we hear speeding up. This was actually to slow it down so that it would shrink its orbit and make it more elliptical. And then I learned a new term. It's de-assist. It's a gravity de-assist. So it's a decrease in the velocity in that it's shaping the orbit, it's changing its semi-major axis. But it's doing it so that it can get those close approaches to the sun. It did 7 Venus flybys in the time that it's been out there. It's now at the point where it won't get back out into Venus's orbit, so it won't be doing any more Venus flybys. Each of the periods are 88 days, and there's been 24 orbits so far, and there's still more to come, obviously. So I think that was one of the things that Nikki Fox explained in her talk at Rice that I'd never thought about. It's like, oh, it's like you're going this way, but you want to go that way. You got to change your velocity somehow. Okay. It's really hard to put into terms how close the spacecraft got to the sun on its closest approach back in December of 2024. So I'm a really big fan of analogies. So there's a very short video I have to explain it using an American football field. So if you put the sun at one end zone and the Earth at the other end zone, I'm not a huge football fan, so I apologize if I use one of the wrong terms. So Mercury is at the 35-yard line for the sun. Venus is at the 28-yard line of the Earth. And the corona extends out to the 15-yard line. Is that within, what's that called? Field goal range? I don't know. So Helios 2 was the spacecraft previously the closest to get to the sun. And that only got as far as the 29-yard line. So Parker Solar Probe is going to the 4-yard line of the sun. Pretty much a touchdown. Yeah, definitely within, hopefully a touchdown and a 2-point conversion. Did I use that right? So yeah, literally flying right through. Remember, the corona went out to the 15-yard line and it's at the 4-yard line. The closest approach, to put it in perspective, was 3.8 million miles from the surface of the sun. And I have the images from that close approach to show you. So it really was close, touching the sun. Okay, so to answer your question, some of the discoveries and observations. Now, I really had a hard time narrowing down what to talk about. I don't know where I am on time, by the way. 10 more minutes? Got it. Okay. I just realized there's no clocks and my watch battery died. Sorry. Okay, so to distill down all of the science that's happened into what can I talk about in the time frame that I have was really challenging, especially because I could do 6 more talks on this, but y'all would get tired of listening to me. Okay, so one of the first things that I thought was really cool, and I have to kick off with this, is they encountered a brand new phenomenon not seen before, and they even had to name it because they'd never seen it before. It didn't even have a name yet, and these are called switchbacks. So there's particle streams coming off of the sun that they're being flung out at these incredible speeds, and then suddenly they do a U-turn, come back to the sun. Sometimes they're heading towards the sun again for just a few seconds. Sometimes it's hours. And then they suddenly do another U-turn and head back out. That had never been observed before. And so they called it a switchback, which in hiking terms to me makes sense if you're switching back. Obviously, there's a couple of theories on why that happens. Maybe something about one of the magnetic loops catches it and pulls it back, and then it escapes again. There's some kind of magnetic explosion that is the part that throws it back out. Some of them think it's like when you have a hose and you're watering the yard and your hose gets kinked. It's kind of that thing, so it's traveling along something. And others still just think that it's being influenced by turbulence in the solar wind. So something is happening in the solar wind that pushes it one way and then it goes another. It's to be seen what the answer is. These are theories at this point. It was just discovered by this mission. And so they had to give it a name, and they're going to figure out what it is. The next one, this was news to me. I wasn't even aware of this, but apparently there is an inner solar system ring of dust that I didn't even know was there, but it has been officially imaged now by Parker Solar Probe. Something that I remember one of the papers talking about is that it was assumed that there would be an area around the sun where there wouldn't be any dust because essentially it would be being kicked out by all the solar wind. And when Parker started approaching the sun for the first couple of close approaches, it was encountering a lot more dust than they anticipated. Of course, the spacecraft is built to handle those things, but it was contrary to what the expectation was. So throw those textbooks out because now they have wrong information in them. But it was able to directly image that ring of dust that had been hypothesized, I guess, is the best word I can think of for it. The solar wind. So it's been known that there were two types of solar winds. Think of it as slow and steady solar wind, and by slow we still mean 220 miles per second, which isn't really slow. And then there's fast solar wind, which is about 430 miles per second. And, you know, obviously that's been observed just from the other missions that we've had. You can see that kind of a thing, and you can measure there's two types, or there's two waves of particles that you get with solar wind. What is now known is that the slow solar wind is actually twice as dense as the fast solar wind, and its particles vary more in the solar wind is way more variable than when you look at the particles in the fast solar wind. And they encountered particle data that showed the solar wind to be way more complex than initially thought. And again, this is why the spacecraft had to go to the sun, because we can measure the solar wind near us, but we had to measure it at its source, and they discovered just how different it really was between the two types of solar wind at its source. Did my video not play? Sorry about that. Oh, it did? Okay.
It ran through.
Oh,
So
I thought I had it looped.
So the higher solar wind would be more intermixed or more homogeneous than the slow solar wind. There's more
The particle composition of the two. Yeah. Okay. I saw on all the listservs how everyone was excited about this comet. So I went and looked, and Parker Solar Probe had actually observed it. So I thought I might. There we go. So obviously it's the stitching in the video. I don't know how to make it replay. Oh, there we go. So Parker Solar Probe observed the comet 3I Atlas. I know everyone was kind of excited about that one. So, all right, as promised, closest ever images of the sun, 3.8 million miles. We're at the 4-yard line. And this is a video made from the Whisper instrument, obviously. And this is during its 430,000 mile an hour pass in December of 2024. And it is just the highest resolution imagery of the, no, I need you to play, please. I was trying to play it. The laser pointer thing is in my way. How do I get it to play? Hello? Oh. No. All the other ones played. This is the most important one. Please play. It should have a play button at the bottom. At the bottom over here, sorry. There we go. Oh, thank you. That would have been heartbreaking if it didn't play. So this is as it's going around the sun, and it's playing or capturing images of the streaks are sunlit pieces of dust. They can also be cosmic rays or other types of high energy waves. And then you can see this string of just normal solar wind going at normal. And then you have some kind of high energy event going on that bottom half of it. I'll play it again if I can make it play. There we go. So that is a huge solar particle ejection, obviously, there in the background. You kind of see the steady stream from the solar wind, and then you've got all these other high energy particles flying past in front of the spacecraft.
So that's one photon that's going streaking across right there?
Not a photon. It's like a piece of dust that's illuminated by the sun, or it could be some kind of energy particle. But yeah, so to give you kind of a context, one of the first things that I looked at when I was watching this is what time frame are we talking about? So it ends at 3:35 and it starts at 8:30. So 7 hours. So this is a 7-hour time lapse of events at the sun as it's going through the sun. Thank you for fixing that. And then to end, I wanted to bring this one up just because I think I just really enjoyed this picture. But this is a whisper image of Venus during one of its first flybys. It's not a Venus mission, but it still made 2 discoveries of Venus. So the brightness around the edge of Venus is something called night glow. I'd never heard of this before, but apparently when the dark side of Venus, like when you go between the dark side and the light side of Venus, oxygen atoms high in the atmosphere will actually cool and reform into oxygen molecules on the night side. And so this is a glow from that process. I'm maybe not explaining that correctly, but I would definitely encourage you to look into that because it just sounded really fascinating. And obviously the streaks are cosmic rays, so it's radiation. Could also be dust illuminated by sunlight. The other thing that surprised the scientists is that WSPR saw through the cloud cover of Venus down to the surface. And so this dark area is actually it's the region called Aphrodite Terra, and it's a highland on the surface of Venus. And so they weren't really expecting WSPR to be seeing through the clouds of Venus, and it still was able to do that. So essentially, WSPR caught a thermal emission map of the surface of Venus. So what's next for Parker Solar Probe? There's still more passes through the sun that are planned throughout this year. Obviously, if you've gotten excited at all about it, I would encourage you to check out the websites and whatever. Social media. I forgot the word social media. I'll just throw it out there. Whatever. So definitely there's still more to come. And the great thing about this is the science missions are the gifts that keep on giving because more and more scientific papers will be coming out. They were having conferences yearly to go over the discoveries discovered from the mission. And so, the science will start trickling out from the mission the longer the mission's been out there because they have more time to digest the data. So thank you guys all. There's a QR code to get to one of the main NASA websites for Parker Solar Probe. As I mentioned, this is run by Johns Hopkins Applied Physics Laboratory. So they have a website for the mission as well. And yeah, that's it.
Couple questions.
Okay.
Is there an end date that they're projecting this mission? How far it might go?
I know every science mission has is it phase E or phase F? I think it's phase E. Phase E is the active time of the mission. And there's usually a timeline for it. And then if it gets an extension, it'll have an extended mission, kind of like Kepler had K2. I don't know the date on that. All I know is that there's 2 more close approaches this year. I didn't look beyond this year.
It's like some of the other probes and it goes way past its design life.
That would be fantastic.
In some of the results, have you seen any research coming out of it relating to the discovery of the heavier particles? Like you mentioned it, there's the one probe that could do electrons, protons, and alpha particles, but like what about carbon and some of those you mentioned?
I would need to go back and look. I usually don't see those because I don't know, like, I look more for the imagery stuff because I can process that a little bit more easily. But yeah, especially with the organizations that have SWEEP and fields, they would be the ones you'd want to look at. I think it was Harvard that did SWEEP, and then the Naval Research Laboratory did fields. I have that backwards. Those organizations will have their scientific papers coming out with their authors on it from the mission. So I would look there to see.
Yeah, because for space electronics, you mentioned, right, that it's those heavier particles
Yep.
and they're the big problem jobs.
Mm-hmm. Yeah, that would be interesting to look at. I hadn't really looked at those.
Yeah.
Yes.
What's the limiting factor on the life of the vehicle?
As always, I'm sure it's something in the realm of, it's obviously very radiation hardened, but you never know. At any time, something could break in that realm. I'm not wishing that on the mission or anything. Also, propulsion, it can only take so much propellant with it as it needs to correct itself. Usually when a spacecraft is nearing the end of how much fuel it has on board, you'll see things like how Cassini was deorbited so that it was done in a controlled manner. Let's see, I don't know. For Parker itself, I don't know specifically what would limit it, but those are two of the more common reasons why an extended mission might end. Oh, I thought he was raising his hand. Mhm.
The radiation hardening
Mhm.
portion of it, when it was being designed, how here on Earth are we able to simulate the 2,500 Celsius?
Oh, okay. No, that's the heat aspect of it, not the radiation shielding. But they, if you want me to, I can address the heat shield. So they did obviously lots of computer modeling with this carbon compound that they were going to build the heat shield out of, and they actually did what they called it a blowtorch test. It was obviously way more sophisticated than that, but they had a blowtorch aimed right at the heat shield, and they had thermal sensors on the other side, and noticed, okay, yeah, we're going to be good here. And of course, they're going to do all kinds of research on the different materials that were available at the time to see which could handle it the best. And that's usually what happens. They'll do a test of all the different materials after doing modeling and whatnot. And then obviously you've got to do some actual testing of it.
Yes.
We out of time?
No, it's,
Oh.
any other questions?
Oh, you wanted me to, oh, go ahead. Oh.
Yeah.
Oh, yes.
What was the science that cracked the code on figuring out what materials compositely work to be effective in technically?
The heat shield? That's a good question. I'm not sure I know the origin of where that carbon compound came from, because a lot of times it comes from like industry, right? Or there's some need for it. So I don't know what that driver was for someone to say, oh, let's do this version of carbon compound, and I bet it can withstand the heat. I actually don't know the origin story, and that would be fascinating to know. You have research to do. No, I'm joking.
I looked up on Stellarium, it's a planetary software
Uh-huh.
that bright dot in the sky is probably Venus.
Oh, okay.
If that was the rocket
Yes.
that launched it.
Yes, you can see the mission patch on, well, patch,
It launched in August.
August of 2018.
August of 2018. And I looked at the evening sky or sunset and sunrise. In the evening, Venus was visible.
Yes, I got my wish. It's poetry. Thank you for doing that. That's amazing. I appreciate that, and I appreciate it wasn't a question.
I think you can find an answer.
All right, thank you for doing that. He gets the gold star of the day.
Do you have,
Oh yeah. So also I had to show off my sun plushie that I have on my desk always with me. Makes me happy. So as part of my program with JPL, I can say, hey, I'm gonna go do a talk on the sun, and they'll send me materials. So I have these really cool solar images, and they're Parker Solar Probe facts on the back, and then it has a little spot where you can see the Earth to scale, which is nice. And then these postcard packs, which there's one for every planet in our solar system. Oh, sorry, I missed your microphone. And then I have, because I love SDO so much, I have these ginormous SDO posters.
Nice.
So I have a bunch of those. So if those are free, please take them. I'll have them out on the table during the break.
All right, let's give Amy a
Thank you. Take my son and my plushie.
So you'd asked about radiation hardening. That's similar work I do at NASA. And the way they harden electronics is you take, the actual electronics and you stick them in particle accelerator beams and you irradiate them. So you can, like particle accelerators, right? You can pretty much simulate most of the highest energies in space on the ground here.
Okay, so.
And so, yeah, you literally go try to break them and characterize their performance and things like that. All right. So we don't have all of the items here, but Rick, did you bring any sky and telescopes?
Yes,
You did?
and,
Okay.
and let me let you know what's going on.
Yeah.
We took the library, the DVD library, and we decided we're just gonna distribute them out to everybody as they want, but we're gonna do it the same way we're doing the sky and telescope. I'll bring 5 of the DVDs every month, along with 5 of the Sky and Telescope magazines. So you're welcome to them up there. Try to take one each, so don't just always spirit ones. And I also took some of the really good ones, and actually they're here, but I'll be giving those out so we can put them in the box for giveaways with the tickets starting next month.
Okay.
So no tickets today.
When Doug's back.
Yeah, we don't have those today, but yeah, thanks a lot, Rick. That'd be great. So earlier I'd mentioned, I forgot we had this graph. This is for the meeting after the meeting for those that have never been. We just head up, if you leave UH Curl Lake, you go north on Middlebrook all the way up to Clear Lake City Boulevard and turn left. The Mod Pizza's in that complex next to the HEB. So everyone's welcome to come, and we hope you do. And so, yeah, right now we're going to take a short break, maybe 10 minutes. So feel free to come look at the items Annie has. And Rick, if you want to show anything there. I forgot if you said you had magazines or not.
The magazines are all
Up there?
in the
Okay.
corner, and so are the DVDs.
Okay.
Help yourself.
All right, we'll start back up in 10 minutes. Thank you.
I'm just gonna mute the microphone temporarily.
Yeah.
There we go. They're going down.
Even when it did.
Here is just a matter of
That's what we did there. Yeah.
maintaining.
It's a good advertising.
Oh, yeah. But that's just.
Okay. Hey, everybody. Let's see here. Did you get that
You
started?
can talk.
So next we're gonna have Al. What's up in the sky, Al? Tell us all. What?
The zenith.
Don't just say stars.
Doug always makes sure you clap as the speaker starts, so he feels welcome. Yeah, because it's scary up here. Oops. There we go. Okay, I do this kind of color. Good, at least we're on January. That's weird. I didn't know I left that picture in there. Okay, so I practice on my pronunciation of some of these complicated words. So quadrantids. It just doesn't work for me. I see like quadratic in that. So anyway, we just kind of missed this. The peak was around the 3rd, really, not the 2nd, around the 3rd or the 4th. But there's some lingering period here through the 13th, which I guess we got a few more days. I'm still frustrated over the meteor showers not being more concise and more predictable and more possible to see. But someday. Okay, very first object. I've kind of favored globular clusters and kind of avoiding some of the nebulosity that we have out there, because I got kind of bored with using filters. It's really time consuming. But anyway, so I started with Pac-Man cluster. So there's 2 images here. This is the one on the right's a little bit more zoomed in, and the left is a little bit more open. And if you look right here, you can see this is the Pac-Man feature. There was a previous name, but it got changed recently since the Pac-Man game came out. So let's see what's next. So this is an open cluster, and I think you can see this pretty good with binoculars. Open clusters are a little bit trickier with binoculars. It depends on what power you have, and you might need to look at it and see what the field looks like in your binoculars on something like Stellarium, so you can kind of match it up, because these things have a tendency to tilt and rotate, and so you might not see it quite right. The second object is another open cluster. This is in the southern sky. This particular month, I didn't pick one particular region of the sky alone, and so you'll see a bunch of variety. So I didn't go pronounce this, but Petus I figured would be pretty easy. And there's 2 open clusters, M47 and M46. So I believe 40, I think they're reversed. I think 47's on the left and 46 is on the right. But what I thought was really interesting on this set of open clusters is there's a planetary nebula here, and you can see this in the right-hand picture. And I looked it up, and it's magnitude 10.8 to 11, but also it's not actually in the cluster. It's actually in the forefront, but it's there. So if you have a reasonable size telescope, you can probably find the open cluster pretty easily. And then this is one way to find a planetary, especially if you're like manually moving your telescope. So that's kind of neat. Let's see what we have next. So now we go from binocular objects to telescope objects. So this I thought was really interesting because this is NGC 3180, but it actually has several designations. It actually has 3181 and 3184. Very interesting. So that's because they gave it different designations for different aspects of it. There's quite a bit of H alpha in this galaxy, and so that's what one of the numbers refers to. And as usual, I try to have a picture that kind of represents what you'd see in a telescope, which is the left image, and then the right image is, of course, like the Hubble or Chandra type image. So, highly highlighted and very interesting. I love that oval kind of look to it. like to see that in the observing picture, like on the left. We'll have to check that one out. I don't know that I've looked at that galaxy, so that'll be interesting. Next one, I have a little video and on the next page. And so this is called Tiger's Eye 2841. And let's see what I wrote as notes. So what's interesting is the pink color that you can find in galaxies often is missing in this because there's a lot of young hot stars in here, and the young hot stars tend to push away some of the leftover nebulosity in a galaxy, making the color look a little bit different. So that's neat. So let's see if the next page, the video works. I like this because it gives you like a visual into the galaxy. Certainly visually, it's a little harder to see some of the texture like this. I don't know, I didn't record how big this galaxy is, but I don't think it's super large. But in a photograph, you could do this. In a photograph, a good high resolution photograph, you could do some zooming in and look at different portions of it and not just be looking at that wonderful, cool, zoomed out picture that everybody seems to like. But in this, I just see so much texture and stuff. There's a few galaxies with a large telescope that you can see some of the nebulosity within the galaxy, like particular regions, and then different, I don't know about globular clusters. I think that there's a couple of galaxies you can see globular clusters in it. And this is one of my things I want to work on this year is look at a couple of these. I think it's M101 and another, I can't remember the number of it. Maybe it's M82. You can look inside and see some of the different objects like we see in our own galaxy. Remember globular clusters, open clusters, objects like this are in our own galaxy, but there's a few galaxies you can see them in the galaxy of a faraway galaxy. So the most interesting thing I came across this month was I didn't know these objects. These objects were discovered in 1968. They were discovered late because they're in the plane of the Milky Way. So it was so obscured by a lot of our own local stars and nebulosity that they just kind of went unnoticed. And one of the famous ones is IC 342. IC basically because it was discovered so late, it ended up on a much later list than, for example, the M's or the NGCs. And so this is kind of a neat, like face-on galaxy, IC 342. But there is a group of galaxies, and here's a couple of the other ones here on the right side. I think on the next page I have another little map of this area. Yeah, on the left is the little bit of a map. I didn't look at this too good. It shows you the Milky Way and everything, and it doesn't show you what constellation it's in. I think it's Cassiopeia. But on the right is the list of the galaxies that are considered in this group. So it's kind of neat. It got a little bit overwritten here, but I put this link in here. You can go search it out. MAFFEI is pretty easy. And you can go and search this out. Maybe you can go find more information on it. And I didn't put a QR code on there. That might be something I might try in the future. Next object. IC 2177. So here you go. Here's some nebulosity. The Seagull Nebula. I've never really looked at this one, but obviously it's very intriguing. It has that neat little orientation. And in other pictures, you can really zoom in different parts of this and really do a lot more photography than just like this wide field view. I think, like the pillars and stuff like that, you can get other types of visual pictures. This one is a Mission Nebula between Canis Major and Monoceros. I look at Monoceros quite a lot. There's quite a bit of nice galaxies in that constellation. Okay, last object. I usually hit a whiz banger here. So this is an ARP. This is this list of interacting galaxies. This is NGC 2623. And this is like the antenna galaxy or galaxies. It looks very similar. It's pretty small. Magnitude 13.9, so on a really good night. But with a large telescope, it's kind of fun. It's nice to know of some objects you want to see because you go out to a star party or something, somebody has a big telescope or is doing some photography, and it's really neat to be able to say, hey, let's go spin around and see one of these ARPs or something like this. So if you don't have a big telescope, that's okay. You want to have a good list to go give others ideas And I have a large telescope, and I'm always looking for ideas of neat things to look at, galaxy clusters, neat galaxies like this. And it's a real fun to try to see if you can see these little arms. Certainly this part is very easy to see these two galaxies, but seeing these arms, and when you see them for the first time, you're like, wow, I really saw that. It's something pretty neat. So I have two recent news items. This is a new picture that is another one of these combination pictures of both the James Webb and the Chandra X-ray Observatory. I wished I knew which color was which here. I'm assuming the blue might be James Webb because of the type of detail you see there. The James Webb, remember, does infrared, and the Chandra is X-ray. And so one of them sees small particles and one of them sees big particles. And so you get a mixture of both the like gaseous part of nebulas and galaxies. And then you get the particle part, which is really neat because that's two things we couldn't see before. We could either see one was more the visual components of things, or we've started to do X-rays, but the Chandra is really wonderful at getting really, really great resolution. The next object and the last one is this object. I thought was really neat, ASCAP. Australia has a square kilometer array pathfinder, and I believe it's just the same X-ray type of array for imaging. But it's really neat. It has several parts to it. There's a core, there's inner knots, and then there's this box type shape in here. And then these lobes are actually X-ray wings, like maybe, a lot of these objects, they produce these pictures and they're like, they want to get it out into the public, but it might be months later that they study it and they try to figure out exactly what's going on. The only problem there is that usually there's not any background information where that comes back to us and we go, oh, that's what they discovered. Because so many of these ideas, they just want to, I don't know, maybe if they put it out into the public, then it gives others an opportunity to go and study them, gives other people idea for research papers, stuff like that. So then maybe it's a couple of years before we actually get more background information. We learn more about how this mysterious universe works. That's all I have, and I don't usually ask for questions, but if anybody has a question. Thank you.
Thanks, Al. All righty, let's see, who do we have next? Rick Slater. So this is a do-it-yourself astronomy topic. So Rick will come talk to us about light frames, dark frames, flats, and bias frames, and their role in astrophotography. And that's how you do the mouse right there.
Yeah.
All right.
Okay. And how do I change? I change the picture.
Just up and down right here.
Oh, up and down right there. Oh, okay. Oh, that'll work. It looks different. Okay. Okay. Well, when Doug asked about having giving some of these shorts, I was going to try to do something. And I thought, what am I working on right now that's giving me problems? So I came up with looking at what all the different frames that you take to really correct for the sensor. And at the same time, your light frames too, which is really the picture you're taking in the sky. So I put together a primer. It really just introduces you to what the terms mean, kind of what things look like, and how do you actually shoot those, and what do you get out of it. So, okay. So first thing, and here, and I'm just gonna promo myself. This is the first color picture that I actually made happen with the computer. It was made from 2 hydrogen frames, 2 oxygen frames, and 1 sulfur frame. And I was finally able to get that computer program going so I could actually take it. So, and I worked real hard on it this week because I wanted to at least have that in there. So when you're taking these frames, what you're doing with really all of these frames, and the fact that you take multiple frames to do it, you're compensating for what the sensor just isn't really capable of doing with the type of photography that you're doing. And the example that I always give is, if you were out in the desert and you've got some big lights and you've got a car and you've got your camera and you shoot that picture, it's going to come out perfect. You're not going to have any imperfections. The sensor works perfect. Everything's great. Now get in your car and drive 5 miles away and shoot the same picture. Guaranteed, with all the black and all the long exposures, the 5 or 10 minute exposures, there's no way that that sensor can really handle it. So that's the reason that we do all these different frames. And there's four specific ones that we use for the compensation. But at the same time, the pictures you're taking of the sky itself have to do a little bit of work too. And that's why you're always wanting to take as many multiple frames as you can. There's 2 kinds of noise that you're really dealing with. You've got the random noise, which is corrected with those light frames, and light frames are the pictures you take of the sky. And what happens is, if you just took one picture and you had comet or falling stars or passing clouds or a satellite going through, it's going to ruin the picture. So that's why you want to have multiple pictures shot, or multiple frames shot, so you can go through it. And if you've got 1 or 2 where there was a satellite that went through, you basically just delete those. At the same time, you've got non-random noise, and that non-random noise is something that's always going to be showing up. And you want to compensate for that. And what I'm going to do here, I'll go through each one of the 4 and kind of talk about what they do, how you shoot them, and I've got some pictures that kind of show what they actually look like as you're shooting them. First thing, computer does all the magic for you. You shoot these, but there's no way you can do anything except put them in a computer and have it do it for you. And I won't go into this too much, except to show that in your final image over here on the upper right, what it's doing is, you've got your dark frames and you've got your BIOS frames, and those are combined together by the computer. They give you, they call it a scalable dark. It's called different things. And it ends up going up to the dark subtracted image, and then it ends up in the final image. Whereas down at the bottom, you've got your flats and your dark flats. The computer combines those, and we'll show you why. And then that goes straight to the calibrated image. But it's all done by itself. I was amazed how fast the computer works when it's putting it together. First, you've got your light frames, and those are the pictures you're taking. And you want to eliminate that random noise. We talked about that, meteorites, planes, or satellites, and that type of thing. The one thing in going through probably 25 YouTubes and a book or 2 on how this works and what you're going to actually do with it. As I said before, with the light frames, you're going to look at them, and if you have a bad one, or you have one that somehow it wasn't tracking properly, what you do is you take those and you get rid of them. You just get rid of them yourself. Now, the computer program can be adjusted so that it says, hey, just use so many frames, and it will eliminate the bad frames. I think the default on mine is it automatically eliminates 3 if you have 3 extra frames. And so it'll see a satellite going through and it'll eliminate it. Okay, we talk about sensor temperature a little bit. The sensor temperature, and I've got a chart I'll show you in a minute. The sensor temperature is critical to eliminating a lot of the electronic noise. And so you want to keep that, if you can, at about -4 degrees Fahrenheit. At -4 degrees, you've done the best you can in eliminating a lot of that noise. Now, mine and a lot of the newer ones have, in fact, mine has something they call a double refrigeration unit or whatever, and it will maintain it. Although if it's 80 degrees out, I can't get -4. I get about 3 or 4, but it's close enough. But if you do have that on there, it definitely helps eliminate a lot of the electronic noise we'll talk about in a minute. And the consistency with that is also critical. And here we have a light frame, and I'm going to divert for just a second and show you a little bit why I kind of went to going with the different black and white camera with the different filters. And to shoot in my backyard, because of the crappy light pollution, I have to shoot with the hydrogen, oxygen, and sulfur filters, which also forced me to go to 10 minutes per exposure. And to be honest with you, there's a few things I really should be going to about 15 minutes on. And so in doing this, you basically, I love doing the color, and I've only done a little bit, but I really enjoy doing the color. But when it comes to kind of identifying things and seeing things, I found that going with the hydrogen, oxygen, and sulfur filter, I was able to see some stuff. And I'm not sure, I don't think you're going to be able to see it that well here. But when I looked at this filter, and this is the hydrogen filter, when I looked at this filter, I saw this kind of a modeling lighter gray coming off, and the whole right side is full of it. And it's not even, it's, kind of here and there. And so I suspected, hey, maybe this is, it's hydrogen. So maybe it's the hydrogen signature. So maybe it's hydrogen out there. And not really knowing anything, but just seeing something that was interesting. So I went and I looked at the oxygen filter, and this is what I got. And although it's hard to see, everything on your right now is very dark. In fact, all the way around it, it's very dark. And so I'm not seeing that. So that's where I suspected, hey, that hydrogen is really going out, far out from the Orion Nebula. And what I want to do now is I want to do a little research and find out what's really going on there. And so that's what I'll be doing now, maybe for my next 10-minute. And so what I did from there was I went ahead and just started trying to figure out what am I actually looking at. So I went ahead and found out that Orion is about 24 light years in diameter. To give you some perspective, our solar system, if you go out to the end of the Oort cloud, you're about 2 light years. And actually, if you go out to about Pluto in diameter, it's less than 1 light year. And yet this hydrogen has gone out and it's 60 plus light years. And actually, after asking someone today, they said, well, actually, it's way out there farther than that too. So that to me was interesting. And that's kind of why I'm doing the black and white. And now that I'm learning more from doing the hydrogen, those 3 different filters, I'm seeing some things. So that's kind of where I'm heading, but I like to do the color too. Okay, back to the topic. Okay, sensor temperature. This gives you an idea and of just how having the temperature lower really helps in getting this electronic noise off the sensor. And I've got the 2600, I guess, and it looks like identical to it. I think there's a ZWO 1500 that has the cooling unit too, it looks almost identical. So if you can get the temperature down, that's really critical and important. Dark frames, there's two things that we're looking for there. Electronic signature, and I'll call it amp glow. That's what they commonly refer to it. It's really related to the components used to read out the signature, and I got a picture that'll kind of show it in just a second. The other one is dark current, and that's sort of it's a small electronic current leakage is what they call it, and the temperature definitely affects that. It's pretty much even across the sensor. And I will say that with dark frames, there's a big controversy now. Some people don't even do dark frames because a lot of your newer cameras don't deal with amp glow, and the dark current is well controlled compared to what it was, say, 15, 20 years ago, especially with the CCD cameras. And so, okay, a little bit about this. I won't read this as much as just have it on there. 3 of these, you actually put the lens cap on when you're making them. And one of them, you have a light, and I'll show you how I do it, a light at the end of the telescope. And so for dark frames, a lot of people don't even shoot them anymore. And to be honest with you, what I learned was I could probably get away without it, but for right now, I'll continue to do it. Okay, here you go with amp glow. And this is where the components connect to the sensor. And this is and that's the ASI 880 or 183, I guess. Yeah. And then this is 120 seconds. That's 300 seconds. And that would be 600 seconds. So it's something that you would absolutely have to have if you've got that kind of a, if you've got that kind of a problem. So I went ahead and I shot my own, and I ended up with that. No amp glow whatsoever. And to be honest with you, these are only 3 megabyte files because that's all I can, that's all I can pull off that. And when the actual frames I'm shooting are 50 megabytes. So although it's probably hard to see on there, as you look at this, there's a little bit of modeling you see in there. When I put it on the computer and I brought it up at 50 megabytes, it is absolutely smooth, but it's not black. And if you look at the bottom there, that's black. That's what you really want. What you're getting is some of that electronic noise that they call it dark current. That's going to be even across the whole thing, and you want it eliminated. Okay, flat frames, and there's 2 different ways. When I first started looking into it, they said, and I did it this way, they said put a t-shirt over the end of your thing and then have some sort of a light over the top of it. I investigated a little bit more and found out that what people really do most of the time is, and I bought a $20 tracing light and just stuck it over the end of the telescope and did it. And it turned out that my computer on the telescope actually has an auto function that automatically comes up with the time. So I didn't have to try to guess at what time I was going to have. So the whole deal with flat frames is you're correcting for vignetting and dust spots. And the one thing I did learn, I hadn't thought about much until I started doing this, is just before I start shooting, I clean the end of that telescope, because I don't know how many times I've had the lens, I cleaned it, put the lens cap on, took it out, and then I took the lens cap on and off, and I looked at it, and it's full of dust. So whether it instantaneously did it, I don't know. But they also said, you're never going to eliminate dust. So, hey, that's why you got to do these light frames. And I'll show you what that means in a second. The other thing is vignetting. All telescopes vignette just a tiny bit, but it also depends on what size, what size sensor you have. And there's some other things I can show you a picture of in a second. And I've got on here just a little bit about, how you shoot it. They tell you shoot as many of these as you can. The bottom line is, some people said 5 is enough. Some people said 80. Some people said 40. They were all over the place. So what I've done is, because they're really fairly simple to do, I've gone with like 60 and just done 60 and shoved it in there. Unfortunately, with the light frames, in my backyard, I've got the house here and I've got the overhang to the garage here. So that's it. That's all the time I have. So if I get 5 or 6 frames of all 3 filters at 10 minutes a shot, because it's a half an hour per picture, that takes a little bit of time. So I don't get that many of them. I'm looking forward to actually going out on one of these trips where I'll have a lot more time to do it. But at any rate, let's see what they look like. Okay, so this is something I took off the internet. It was an example. And what you had here is, you can see the vignetting in what they shot. They also mentioned in there that the 2-inch filter was too small for the sensor. That also contributed to the vignetting. Then this is the picture, the flat frame that they shot for that. And all it's doing is it's showing the signature for the telescope. And then after they applied it in the computer, that's what they get. The vignetting's all gone. And then I did mine, and I came up with this, which has still got some vignetting in there. It's still there, so you still need to do it. Okay, dark flat frames. Dark flat frames remove the dark current, or that little bit of, electronic noise that's across the thing, from the flats that you just shot. And it shows you here how to do it, and 20 to 50 is what I stick in there. So let's see what that looks like. And the dark flat frames look like this. And again, it's much better at 50 megabytes. It's just much smoother. But very little problem there. Bias frames. Bias frames is where you turn down, you've got your gain turned down to practically nothing. You're looking at 1,000th of a second, and you're going to shoot those. So in theory, it should be the smallest amount of electronic noise across the frame. And yet, even when you do that, I put black there on the right, and this is the best. This is the best you're going to get. It does have, it is, and in the 50 megabytes is absolutely smooth across there, but it is not black. And you've got a lens cap over it, so you would hope that would be there, but it isn't. That's why you have to do it. And it does make an improvement. I'll be honest with you, until I do it a whole bunch of times, I can't tell you how much. Summary points. Number 2, never skip flat frames or bias frames. Also, dark frames and flat frames are often not done by folks just because the new cameras are just so good. You don't have to bother with those. I will say that hot pixels, I figured it's a new camera, it should be really good. I was amazed. There were probably about 15 hot pixels in there, and they're there every single time. In fact, the computer software, you can push a button and it will show you where your hot pixels are. Let's see. Have a cooling unit if you can. It does make a difference. And that's it. Any questions? I didn't put everybody to sleep, did I?
What software are you using for that?
Axle Pixel Processor.
Excel?
Axle Pixel Processor. I think I'm the only one using it. So be honest with you. All I know is somebody said, hey, I hear that's the hardest one to learn. So I was real excited when they told me that. And I will say it took a while, and I'm just doing the automatic part. There's a lot of other things you can do with it, but it is pretty amazing what comes out of it. So, and it does show you an awful lot of information. The thing I really liked about it was with the 50 megabyte frames, you can really zoom in. So anyway, okay, that's it. Thanks.
Okay, let's see here. You had a couple more slides. Did you want to?
No, those were backup slides.
Okay. All right, so I guess David's not here, so I'll try to go through the Star Party news. January 23rd, that's coming up. Looks like we have an event at Seabrook at the Evelyn Meter Library. So 7 to 9 p.m. is what it says here. It's on a Friday, so hopefully we get some volunteers to show up for that. It's a public Star Party. I guess that's the only event. Okay. Next month, Jerry going to be talking about gravitational wave astronomy. Sounds exciting. That'll be here at our next month's meeting. I think that's all we have, actually. Yeah, we don't have the giveaways. Next month, we typically, that's right, Annie's got a few things I'll mention here. She's got a few books that she's giving away, so stroll over here when you get a chance. We do, I know we have a Star Party coming up in April for our club. Typically, we would go, I think, in March, but they're having the Messier Marathon, so you're welcome to go up to Fort McCavitt for that. But I think we'll talk about all these events next month. But we do our next club events, West Texas type events are in March and April. And so yeah, I think that's all we have. Any questions? Yeah, Al, you got a question?
We went by the slide real quick earlier, just because we have a couple new people. Mentioned that they can find the email list on like the website.
Yeah. Okay. Yeah. I that was my fault. I scrolled. I thought it was at the end. Yeah. For the new people here, maybe come talk to me afterwards. I can show you how to get on our email list. We have two web email. One's you get the general announcements and one more club associated with. So yeah, come talk to me. Yeah. So. Mention Mod. Hope you guys are hungry for pizza. Come by and eat pizza with us, and we can chat some more. And thanks for coming. Thanks Annie and Al and Rick for the talks. And we'll see you next time. Thank you. I'll let you shut her down.